How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
You click on a link. A web page begins to bloom into existence on your screen. While it loads, the music you have playing in the background doesn't stutter for even a millisecond. A notification from your email slides into the corner of the screen. Smooth as glass, you start typing a reply, and the letters appear instantly. We just assume our computers are powerful enough to do it all at once. But how does this actually work? What simple rules make this intricate, simultaneous dance possible? Today, on First Principles, we are decoding the single most important piece of software on your computer. The one you look at every day but never truly see, the operating system. The magic we see every day is one of effortless harmony. It's the closest thing to real-world wizardry we have. Think about your phone or your computer at this very moment. You might have a dozen browser tabs open. One is streaming a video, another is updating a live news feed. A separate application is managing your downloads, pulling a large file from a server thousands of miles away. Your word processor is waiting patiently for your next keystroke, while your calendar is running a background process to check for upcoming appointments. All of these individual programs, written by different people at different companies for entirely different purposes, are living together on the same piece of silicon, sharing the same resources, and somehow not tearing each other to digital shreds. This illusion of peaceful coexistence is the operating system's greatest trick. It presents you with a calm, orderly desktop, a grid of icons, a set of windows you can drag around and resize at will. It gives you the sense that you are the master, a powerful user in complete control of a machine that can do many things at once. The reality inside the machine, however, is not a calm democracy of cooperating applications. It's a ruthless, high-speed battle royale for a handful of exquisitely limited resources. Every program running on your computer is fundamentally selfish. It wants everything, and it wants it now. It wants the processor's full attention. It wants all the memory to itself. It wants immediate access to the hard drive. If left to their own devices, your programs would create a digital traffic jam of epic proportions, crashing into each other, stealing data, and bringing the entire system to a screeching halt within seconds. The fact that this digital anarchy resolves into a perfectly smooth user experience is the quiet miracle the OS performs millions of times a second. To truly appreciate the solution, we first have to understand the problem it was built to solve. We have to travel back to a time before the sleek laptops and glowing phones, to the dawn of computing in the 1950s. The first computers were colossal, room-sized machines, monuments of vacuum tubes and wiring that cost millions of dollars, and using them was a profoundly inefficient process. There was no Windows, no Mac OS. There was just the raw, unforgiving hardware. A programmer would write a program on a stack of punch cards, walk it over to the computer room, and hand it to an operator. The operator would feed the cards into the machine, and the computer would dedicate its entire being to running that one single program. From start to finish, that multi-million-dollar machine was a slave to one task. This created a massive bottleneck. The brain of the computer, the central processing unit, or CPU, was incredibly fast, capable of performing thousands of calculations in a second. But the other parts of the computer, like the card reader that took in the program, or the printer that spat out the results, were painfully slow mechanical devices. This meant the expensive CPU spent most of its time doing nothing. It would blaze through a calculation and then have to wait, sitting completely idle, while a slow printer clanked out a line of text. It was like hiring the world's fastest mathematician and then making them wait for 10 minutes after every single equation, while you slowly wrote down the answer with a quill pen. The inefficiency was maddening. These precious, powerful machines were being wasted. The pioneers of computing faced a critical economic and engineering question. How do we keep the CPU busy? How do we stop wasting our most valuable resource? The first breakthrough came with an idea called batch processing. Instead of running one job at a time, operators would collect a whole batch of jobs, a stack of punch card programs from different programmers, and feed them to the computer all at once. A small supervisory program would then run one job after another, automatically, without needing an operator to intervene each time. This was a huge step forward. It was the first hint of an idea that a special piece of software could act as a manager, a supervisor for the hardware. This primitive supervisor was the great-great-grandfather of the modern operating system, but it still only ran one thing at a time. The bigger, more profound challenge remained. Could a computer be made to work on multiple programs, seemingly at the same time, juggling them to make sure the CPU was always working on something? The world needed a conductor for the chaos. To open this black box, we need an analogy, and the best analogy for an operating system is that of an executive chef running a massive high-end restaurant kitchen. The hardware of your computer is the kitchen itself. The CPU is the most prized piece of equipment, a single, incredibly powerful, state-of-the-art stove that can cook anything, but can only cook one thing at a time. The computer's memory, or RAM, is the kitchen's main prep counter. It's a finite amount of counter space where ingredients can be laid out for active use. And the hard drive, or SSD, is the pantry, a vast storage room where all the ingredients and recipes are kept. Now, the software, your web browser, your music player, your game, these are the celebrity chefs. Each one is a demanding, egotistical genius. They all want to use the master stove, they all want space on the prep counter, and they all want it right now. If you just let them all into the kitchen at once, you'd have pandemonium. They would be fighting over the stove, spilling ingredients on each other's workspaces, and stealing recipes from the pantry. Nothing would ever get cooked. The whole kitchen would grind to a halt. This is where the operating system comes in. The OS is the executive chef. The executive chef doesn't actually cook anything. They don't have their own dishes to prepare. Their entire job is to manage the other chefs and the kitchen's resources to ensure everything runs smoothly and efficiently. The executive chef stands at the pass and directs the chaos. They tell one chef when they can use the stove. They assign another a specific section of the prep counter, and they make sure everyone gets the ingredients they need from the pantry in an orderly fashion. They are the master coordinator, the ultimate manager. The first and most fundamental job of this executive chef is to create what's known as an abstraction. This is a crucial first principle. The celebrity chefs in our kitchen don't need to know the specific model number of the stove or the complex sequence of knobs and buttons required to get it to precisely 375 degrees. They just need to be able to say, "I need heat." The executive chef, the OS, hears this simple request and translates it into the complex, specific instructions the hardware needs. This principle of abstraction is everywhere. The program developer doesn't need to know if you're using a Logitech mouse or a Microsoft mouse. They just tell the OS, the user is moving the pointer. The OS handles the messy details of talking to the specific hardware you have plugged in. It creates a simplified, idealized version of the computer for every program to use. This makes the lives of programmers infinitely easier, but more importantly, it establishes the OS as the sole, undisputed gatekeeper to the hardware. No program gets to touch the stove, the counter, or the pantry directly. Every single request must go through the executive chef. This power is absolute, and it's what allows the OS to perform its other critical jobs. With the executive chef firmly in charge, let's look at how they solve the kitchen's three biggest problems: managing time, managing space, and managing organization. This is the real story of the OS, built from first principles. First and most importantly is the scheduler, which is how the OS manages time. We have one master stove, our CPU core, and a dozen chefs all demanding to use it simultaneously. The common misconception is that a computer with one CPU core is actually running multiple programs at the exact same instant. It's not. It can't. The hardware is only capable of doing one thing at a time. The magic is an illusion, a brilliant sleight of hand performed by the OS scheduler. The executive chef solves this problem with a technique called time slicing. They grab Chef Browser and say, "You get the stove for the next 10 milliseconds. Chef Browser frantically starts working on rendering a web page. Then, before they can even blink, the executive chef yanks them off the stove and says, "Time's up." They immediately grab Chef Music Player and say, "Your turn." 5 milliseconds, Chef Music Player processes the next tiny chunk of your song. Then, yank, they're off too. Next up is Chef Word Processor, who gets 2 milliseconds just to register that you pressed the T key. This switching, known as a context switch, happens hundreds or thousands of times every single second. Each program gets a tiny slice of the CPU's time, but the slices are so small, and the switching is so fast, that from our slow human perspective, it appears that everything is happening at once. The chefs in the kitchen have the illusion that they each have their own personal stove, because they are being put on and taken off the real stove so rapidly, they can't even perceive the interruptions. This is the fundamental illusion of multitasking. Your computer isn't doing a dozen things at once. It's doing one thing at a time, but it's switching between tasks with unbelievable speed. The job of the scheduler is to be the fairest possible time slicer, deciding which program gets to run next and for how long, prioritizing urgent tasks, like your mouse moving smoothly across the screen over less urgent ones, like a background file download. The second critical job is the memory manager, which is how the OS manages space. Our kitchen has a limited amount of prep counter space. The RAM. This is where the chefs lay out the ingredients they are actively working with. Just like with the stove, every chef wants as much counter space as they can get. If we let them manage it themselves, it would be a disaster. Chef Browser might carelessly place their raw fish right on top of the delicate document Chef Word Processor is preparing, corrupting it completely. This is what used to happen in the early days of computing. A single misbehaving program could write over the memory being used by another program, or even by the OS itself, causing a catastrophic system crash. The solution is memory protection, and it is one of the most important duties of the OS. The executive chef takes the prep counter and draws chalk lines on it, assigning each chef their own exclusive section. Chef Browser gets this square, Chef Music Player gets that one, and the rule is absolute. You are forbidden from touching or even seeing the space that belongs to another chef. The OS enforces these boundaries using special hardware features in the CPU. If any program tries to access a piece of memory that hasn't been assigned to it, a loud alarm bell goes off inside the CPU. The OS is immediately notified, and it acts like a bouncer. It instantly freezes the offending program and shuts it down before it can cause any damage to anyone else. This is why today, when one application crashes, it usually doesn't take your whole computer down with it. The OS has confined the failure to that one program's protected memory space, cleaning up its mess without affecting the others. The executive chef has escorted the disruptive chef out of the kitchen, allowing everyone else to continue their work uninterrupted. The third job is the file system, which is how the OS manages organization. Every computer has a massive pantry for long-term storage, the hard drive or SSD. At a physical level, this pantry is just a colossal, disorganized heap of billions and billions of tiny storage cells, each holding a 1 or a 0. There is no inherent structure. It's like a pantry filled with unmarked jars of individual spices, with no shelves, no labels, no recipes. Finding anything would be impossible. A program can't just say, "Go get me the file named my_report docs." The hardware wouldn't know what to do. This is where the OS file system comes in. The executive chef comes into this chaotic pantry and builds a comprehensive organizational system. They install shelves, create aisles, and most importantly, they create a master ledger or index. This system is what we experience as files and folders. When you save a file named my_report docs, the OS finds a bunch of empty jars in the pantry, puts your data into them, and then writes an entry in its master ledger that says my_report docs lives in these specific jars, on these specific shelves, in this specific order. When a program later asks for that file, it doesn't need to know anything about jars or shelves. It just gives the file's name to the OS. The OS looks up the name in its ledger, runs around the pantry, gathering all the correct jars in the right sequence, and hands the complete, assembled document to the program. It creates a simple, logical structure, the hierarchy of folders and files you navigate every day. Out of the raw, unstructured chaos of the physical storage device, it manages the complexity so the programs don't have to. The scheduler manages the dimension of time, the memory manager handles the dimension of space, and the file system conquers the dimension of organization. Together, they form the foundational pillars of any modern operating system. We've seen how the OS acts as a masterful manager, slicing up time for the CPU and partitioning space in memory. But now we come to the deepest, most elegant trick in the entire playbook. This is the unseen giant that makes our modern, heavy-duty computing not just possible, but routine. It's a principle that takes the idea of memory management and elevates it to a level of profound deception. It's called virtual memory. Let's go back to our kitchen. We have our prep counter, the RAM, with its fixed, limited size. What happens when so many celebrity chefs show up to cook that there simply isn't enough counter space for all of them? In a normal kitchen, you'd have to turn some of them away. The restaurant would grind to a halt. In early computers, this is exactly what happened. If you tried to open too many programs, the computer would simply say, "out of memory," and refuse. But our computers today rarely do that. You can have 50 browser tabs open, a massive photo editing application, a video game, and your email client all running at once, far more than should physically fit in your RAM. How? Because the operating system is a brilliant liar. The executive chef, our OS, pulls off an incredible deception. Instead of telling each chef how much real counter space is available, the chef takes each one aside and says, "Welcome to my kitchen. For you, and you alone, I have reserved a gigantic private prep counter. It is enormous, far bigger than you could ever possibly need. Work as you please." And the chef tells this same lie to every single chef. Each program is tricked into believing it has a massive, contiguous, and entirely private block of memory, all to itself. This imaginary workspace is its virtual memory space. In reality, the actual physical prep counter, the RAM, is still small and chaotic. The executive chef is just managing the illusion. Here's how the trick works. The chef gives Chef Browser their massive imaginary counter. As Chef Browser starts laying out ingredients, The executive chef quietly finds real empty space on the actual counter and places the ingredients there. The chef keeps a secret map, a translation table, that links the location on the imaginary counter to the location on the real one. So when Chef Browser says, "I need the onion I put down over there," the executive chef consults the map, finds where the onion actually is on the real counter, and hands it over. The celebrity chef is none the wiser. But what happens when the real counter fills up? This is the heart of the magic. Let's say the prep counter is full, and a new chef arrives needing space. The executive chef looks around and notices that Chef Music Player hasn't touched their pot of simmering sauce in a while. Quietly, the chef takes that entire pot of sauce, carries it to a freezer in the back room, our much slower hard drive or SSD, and puts it away. On the real prep counter, where the pot used to be, the chef leaves a tiny note that just says, "Sauce is in the freezer." This frees up space on the counter for the new chef. A few minutes later, Chef Music Player says, "I need to stir my sauce." The executive chef sees the request, looks at the counter, and finds the note. An alarm goes off. This is called a page fault. The chef then says, "One moment," runs to the slow freezer, retrieves the pot of sauce, finds another section of the counter that isn't being used, perhaps by moving someone else's ingredients to the freezer, places the sauce there, updates the secret map with the new location, and then finally hands the pot to Chef Music Player. This process of moving data between RAM and the hard drive is called paging or swapping. From the chef's perspective, there might have been a slight delay, but their sauce is there, right where they expected it. They remain blissfully unaware that their ingredients just took a round trip to a freezer in another room. This is virtual memory. It's a complex system of illusion, mapping, and swapping that allows the OS to promise every program a vast private memory space, while juggling the limited physical RAM behind the scenes. It's the reason our computers feel like they have almost limitless memory, even when they don't. It might slow things down when the system is under heavy load. That's the feeling of your computer thinking as it shuffles things to and from the slow freezer, but it prevents the entire kitchen from collapsing in failure. It is a beautiful, elegant lie. So we journeyed from the seamless magic of a modern computer desktop back to its chaotic, competitive core. We saw a world of selfish programs, all fighting for a few precious resources. And in the middle of it all, we found the conductor, the executive chef, the operating system. We learned that the harmony we see on screen isn't an accident of powerful hardware, but the result of a brilliant and tireless manager enforcing a simple set of rules. The first principle is abstraction, hiding the messy complexity of the hardware behind a simple, clean interface. Then comes the masterful management of resources, the scheduler slicing up time to create the illusion of multitasking, and the memory manager building protective walls to prevent programs from interfering with one another. And finally, the grand illusion of virtual memory, where the OS lies to every program, promising it infinite space, so the whole system can gracefully handle more than it physically should. Understanding the operating system is fundamental because it teaches us a profound truth about modern technology. Our digital world is not built on perfection. It is built on the clever management of imperfection. The hardware is finite, the software is demanding, and the natural state of the system is chaos. The OS doesn't eliminate these limitations. It embraces them. It creates order not through infinite resources, but through ingenious scheduling, clever compromises, and elegant illusions. It is the invisible architecture of order, the ghost in the machine that transforms a heap of silicon and wires from a dead calculator into a dynamic, responsive partner in our daily lives. The greatest achievements of engineering are often not the things that are most powerful, but the things that are most clever at managing complexity.
You've been listening to First Principles. Until next time, stay curious.